Okay. The next topic is before we finish this section, is so-called analytic continuation, uh, which is obviously important, but then uh, uh, we don't directly use it that much. Uh, but sometimes you use it before you know it. Right. It's basically saying that you define a function over a domain, right? And now, if you have another function, this is analytic over this region. You have another function g or g uh, defined over another domain. It's analytic over this domain. Okay, and this they have a overlap. This overlap doesn't have to be finite. It can be just the boundary overlap. That is also fine. Right? But when they overlap, if you find a finite uh, finite line or finite contour along a certain path, you can show that both functions agree with each other. If you over here, easy, let's think of that over this line, then then the function obviously will be the same over the whole region they overlap. And then you can define a function that combines the two functions and define over both domains. And that function will be analytic. Okay, and then you can call that you can call it another function or whatever that is. So it's saying that, and then the function will be continuous, so because they are analytic anyway. So they are you can find a function that is analytic over the whole domain, and provided that there's an agreement over a finite line segment or something like that. Okay, and I mean when you think about it, this is uh, showing the power of analytic function. Analytic function doesn't need a whole lot of information. You only need just information like on a finite line. If you have this information, they automatically know quite a lot. Right? And this process is called analytic continuation. So you like the F original defined over here, but then you continue this analytic continuation over the larger domain. Okay, and that it's again to that. I mean, this I just state that yeah, obviously, in order to see that there are something there are lots of things you need to prove, but uh, it's sometimes it's useful and sometimes it's conceptually important to remember that what does it mean by analytic continuation, because you forget about that, then sometimes you get a function that has a jump, and that is not good. Okay, so uh, your the textbook, the example is using the Taylor series extension. I think the picture here. Figure 15, figure 11.15. So if you have singularity, and then yes, this is C sub S. Okay, C sub S. And then you can take a Taylor expansion over a circle, say you have a C sub 0, and do a Taylor expansion of the function f, right? And this f has a singularity at Z sub s. And we already talked about that, how you do that. And then basically this Taylor expansion will be convergence over a circle that is with the radius less than the distance from c sub s to c sub 0. Right? So that is what we showed before. So the radius of convergence is uh, from c sub 0 to c sub s, and you can define that circle and find a Taylor series. So once you find a Taylor series, you find a representation of fc over this ring, which is a series expansion. And that one is analytic, obviously analytic because all the power are analytic. And as long as it's convergent, it's analytic. Okay. And yeah, S, yeah, C sub S. This is a singularity. So this is a singularity. So this is your textbook, the picture in the textbook, 11.15. Okay. And we call it C sub 0. This is this circle C sub 0. Right. And now you can choose another point to do your expansion to C sub 1, but not uh, exactly at C sub 0. You somewhere within this circle, choose the point C sub 1. Any point away from C sub 0. And the same reason applies, so you can find a Taylor expansion uh, about this point over a circle with radius less than the distance from C sub S to C sub 1. You found another circle with C sub 1, right? And the reason you can do a Taylor expansion because you already have F, the representation of F, you say Taylor series within this region is analytic. And in particular, you can find all the derivative, any order derivative at C sub 1. You, you understand the once you have a Taylor series, you can do differentiation on any times, as many times as you want, and you find the derivative of C sub of F at C sub 1 as as accurate as you want, and keeping as many terms as you want, right? And then define a Taylor expansion that way. And the Taylor expansion will be converged now over a larger circle, right? So now you extend your domain. Originally, it's just convergent over here. You find a second series. Now it's convergent over the other circle. Then you can combine two functions. One series here, the other series here. And because obviously the two series will be the same over this region, but they overlap. There's a uniqueness theorem that both Taylor series will get you the same F over here when they overlap. Okay, and then you get the single and then function over the larger domain. So this circle plus this circle, or the union of the two circles. Okay, and obviously you can keep going. C sub 2, you find another circle, C sub 2, and another thing expansion, and then C sub 3, and do another expansion. As long as the radius is less than the distance to the singularity, it's fine. Another thing expansion. Right? You can do as many times as you want. Right? C sub 4, C sub 5. Pretty sure pretty soon you can see that if you are patient enough, you can, if this is the only singularity, then you can find continuation over the whole complex. Right? If you are patient enough, at least in principle you can do that. All right. So this is one way to get the analytic continuation. It's not the only way. Not the only way. Another way to get something similar is so-called refraction principle. That is later in the chapter. Uh, if we have time to go through that, that would be in section 10, 11:10. There's a SWOT refraction principle. So that If you define your function above the real axis, you can use the, I mean, if you satisfy certain property, you can define the analytic continuation at the lower complex plane. The, the reflect about the real axis. So that is another way to do it. There are also other way to do it. Uh, Later on, we'll find in like another chapter, in the gamma function chapter, we mentioned that the error function and the error function with complex argument is what many of you do partial physics. Just like me, I do partial physics. Right, there's a function defined in partial physics, so-called partial dispersion function. This is capital C. It's a complex argument. I think it's defined as there's a there's a position in front, but that's not important to our discussion. So to define over an integration of the Gaussian, whatever you use, the C square. This is real, because C is real. You define this function like that, but only for imaginary part of D is greater than 0. You define your partial dispersion function like that. Right? So graphically, it's like you have a complex plane, complex Z plane, whatever that should be, a C plane. You integrate this C all along the real axis. So this is real C. Integrate that. When you define imaginary Z greater than 0, so the singularity is off real axis somewhere, because the imaginary part is positive. So that is the C. If imaginary Z is greater than 0, then you can define it that way. That is how we define the partial dispersion function. Okay, but then in many cases you want to consider the same function, but if Z goes to go below the real axis, or the imaginary part go to negative. And how do you do that? How do you define a single function, a single array function to do that? So this this definition is well defined because this integration is on real C, and the exponential function is well behaved. The exponential minus C squared, so at both ends it dies off very quickly. So this is well defined. But now if we want to extend to, say, we want to move Z, so you can graphically think about you move Z. First you hit the real axis, then if Z is also real, then can you define it like that? Then you get into trouble, right? Because because the denominator get to 0, and your integral is singular. The integral is singular at that point, and that will give you trouble. So whenever you consider any integral, you want to make sure that you look at the integral, whether it's singular or whether it's well defined. Okay, so in that case, when Z hit the real axis, you have a first sign of trouble. And then when it goes even beyond, then again you cannot use this definition. Although now that integration now again becomes well behaved again, but you see that you directly use that for imaginary Z less than 0, then the function going across the direction will have a jump. Okay, and that means it's discontinuous. So once you define your function this way, when Z actually go to 0, or imaginary Z goes to 0, What you want is to deform your this integral going below it. As long as your singularity doesn't cause the contour, that is fine. And this contour integral will still well behave, and the function defined that way will be continuous. Okay, and I see this z goes to negative, the negative imaginary part. You basically go circling, going down, and going around it, and going back up, continue. Right? You define it like that, and you define. Then you extend your original domain to all complex plane, complex value of C. Okay, so that's another way to do analytic continuation. And the idea is uh, for analytic function, there are different ways you can keep extending it, extend the domain, so, explore the whole complex thing except those singularities. Okay,